Thank you. Okay. First of all, I want to say I'm so excited to be here. I don't know, for people who don't know, we had organized the first conference at ICTS 10 years ago. This is very, bringing back nostalgia. So I want to talk about radio emission in low luminosity AGN and basically some of the work that our research group has been carrying on. What I want to stress is that improvement in sensitivity has been a very important factor in getting some of these results. Therefore, the SKA is definitely going to, with its improved sensitivity, is going to really revolutionize the study of low luminosity AGN. By low luminosity AGN, I include Seyfert galaxies and liners. Seyfert galaxies, as you know, were the ones which were first discovered by Carl Seyfert in 1943, and they were identified because of their star-like nuclei and very prominent emission lines in their optical spectra. And liners were discovered much later. They stand for low ionization nuclear emission line regions by Tim Heckman and others. And the difference between Seyferts and liners was that the low ionization lines were much more prominent in liners compared to Seyfert galaxies. And both these class of AGN belong to the radio quiet AGN category. And by radio quiet, I mean that they have these ratios of radio flux density at 5 gigahertz to the optical flux density in the B band. That ratio is typically less than 10. So this 10 came about because of this work which Ken Kellerman and others had done, where they found that when they took this ratio, their sources from the Palomar Bright Quasar survey fell into these two categories very clearly, and the division was around R equal to 10. So this definition has stuck, but I do want to stress that there is nothing very sacrosanct about 10, and a lot of other samples don't really see a very clear divide. So we can keep that in mind. And Kellerman already found that radio quiet AGN probably make more than 80% of all AGN. So this is the vast majority of AGN. They're going to be very, very important when SCA comes around. So for a working definition, we can use this picture. So on the left panel, you have a typical radio quiet AGN, and it's a very famous one, NGC 1068. So here, the green that you see is starlight. In spiral arms, there's a spiral galaxy, and the pink-blue emission that you see are radio outflows. And the first thing to notice is that the radio outflows are small, confined to the host galaxy itself. On the other hand, a small minority of AGN are these very impressive ones that we know of. So this is a very famous radio loud AGN called Hercules A. The optical elliptical galaxy is only of that much size, and the sizes of the radio jets shown in blue are, of course, much larger and go on to hundreds of kiloparsecs. So for the purpose of the talk, we can just remember that radio quiet AGNs are the ones where the jets are small and they kind of are confined to the host galaxies. So the results I'm going to now share with you have definitely come about because of improvements in sensitivity. And this has led us to kind of find out more about the magnetic field structures in these radio quiet AGN, and also the discovery of multiple episodes in AGN activity. So let's start. How it started was in the 1990s when radio surveys of radio quiet AGN and Seyfert galaxies were carried out. So these are, for example, two images from one of these earlier works, which was carried out by Steffi Baum and collaborators. And so these are radio contours of these galaxies, Mercurian 231, NGC 3516. And this was a study carried out with using the Westerbork synthesis radio telescope in the Netherlands. Had some arc-second resolution. Of course, you can immediately see that, comparing it to, for example, Hercules A, the radio structures are more complex. It's not very clear if there is any kind of directional outflow. I mean, maybe here in this is a little bit better, but you don't see much on the other side as well. So this is because of the lack of sensitivity in those earlier observations. And because of this, there was a lot of debate on the true origin of the radio emission from these radio quiet AGN. It was also suggested that perhaps stellar-related processes were contributing to the radio emission in these AGN. And there is some truth in that as well. But as observations have become, more sensitive, so this is a very large array image of 1068, NTC 1068, which I also showed in the previous slide. Now you see a contour image, and you see that there is a directional source, what may look like a jet, but it's still not a simple source. You can see that, for example, this bright knot here is actually not the core, it's not the origin, this is not where the host galaxy nucleus is. The nucleus is actually somewhere here, it is not very pronounced in the radio. This is just a little portion of the jet. So it is complex, but when you start looking at high resolution radio images of radio quiet aging, you start seeing jet-like structures. And because of these improvements in sensitivity, resolution, etc., there is some support to the idea that these probably are agent-driven radio outflows. So let me now come immediately to one of the Seyfert galaxy, which my student Sharmoli Ghosh is studying, and Sharmoli is here in this conference, and she actually has a poster on a very colorful poster on this object. So I would encourage you to take a look at that. So this is radio. So these are very recent observations with the VLA, and now because of sensitivity, we are able to pick up much more weaker polarized emission from these galaxies. So now here is a radio optical overlay. The blue-red emission that you see is the host galaxy. It is a lenticular galaxy, and the green contours are from the radio, the VLA. Here, this image shows the red ticks that you see are polarization vectors with lengths which are proportional to the degrees of polarization. So you can see there is a lot of polarization. This goes almost as high as close to 20%. And then you can see that the inferred magnetic fields for optically thin emission is perpendicular to these vectors. So the B fields may be aligned with the outflows in this case. They seem to be aligned here, but then they kind of flip here. And there are interesting things going on in this particular source also in terms of spectral index. So we think there is a hotspot here and B field compression. Now, this kind of work was not actually possible, several years ago because polarization was hardly detected in most of these Seyfert galaxies. But I think with the improvements in sensitivity, you can now see this. This is an image of the same with GMRT. And again, the ticks are actually polarization vectors. But here I want to stress another point that GMRT not only picks, of course, this primary lobe, but starts picking up even diffuse emission beyond the primary lobe. And I think this is going to be also the focus of our talk today, that as you go to more sensitive arrays, and especially at low radio frequencies, you start getting a much more complex picture of these AGN. What is very exciting is this result that Sharmoli has got on this particular galaxy. So because we had polarization data at one frequency, she eventually got a polarization data with the VLA and also GMRT at multiple frequencies and was able to create a rotation measure image. So this is just the contours are presented here, and the color that you see is rotation measure. So rotation measure is basically is proportional to the electron densities and the magnetic field along the line of sight, magnetic field strength along the line of sight, and then the path length through which the polarized emission traverses. And so you can see here that some kind of gradients are observed in the rotation measure. So the bottom panel actually shows these gradients better. So this slice here across the lobe, and then there's another slice here, are shown in this blue and the red. So what was very exciting was that there is a rotation measure gradient which seems to be reversed in the two lobes of this galaxy. There is also a rotation measure gradient along the jet, which is we believe due to something else, which we can discuss later if anybody is interested. These RM gradients actually have been observed in radio loud AGN, and they have been suggested to be signatures of helical magnetic fields. Because the way you would get a gradient is either a gradient in the electron densities or the B field, the line of sight B field. And there is no reason to believe that you would have this NE gradient in a certain way to kind of produce this RM structure. So one way to interpret this is that the B fields are actually kind of either coming towards you or going away from you in a helical magnetic field structure. So this is a cartoon to show what could be happening. So you have magnetic fields anchored on the accretion disk black hole system, and as it rotates, you have these wound up magnetic fields, which may give rise to these kind of rotation measure gradients. This is very exciting for us because if this is confirmed also maybe by even more data and more sources, this could suggest that the jets even in radio quiet AGN are could be magnetically launched. Okay, so this immediately kind of bridges the gap between radio loud, radio quiet AGN. So it was believed that the radio loud AGN jets, which are very, very large, are probably being driven by the Blandford-Snayak or Blandford-Payne mechanisms, which require this either from the accretion disk or the black hole spinning that you would extract energy into the jets, which are very powerful. If that is also true for radio quiet AGN, then the difference between radio loud and radio quiet AGN is not going to be an intrinsic qualitative difference, but rather a difference in quantities. Maybe it's more quantitative. Maybe there is one factor which has to be changed, which could kind of then produce these different AGN subclasses. So that is very exciting for us. Now, let me show you another Seyfert galaxy. This is NGC 2639. So here is the spiral, rather S0 type of galaxy in the green. And this white contours that you see are actually lobes that are observed with the GMRT. And in fact, so this is at 700 megahertz, and the dotted line is showing emission at 300 or something, 325 megahertz. Previously, there was a radio lobe known in this galaxy, which is shown here in red and actually zoomed out here. That is from the VLA. So the VLA had already identified a north-south bipolar structure of extent 1.5 kiloparsec. But GMRT at 735 megahertz picked up a much larger bipolar structure. And all the VLA emission is actually confined to the core of the GMRT image. And this galaxy, at the core of this, when was looked at even higher resolution VLA data at using the VLA-A array, there's another bipolar structure in a completely different direction. And similarly, the core of that with VLBI or VLBA, very long baseline array, finds that there is a core structure in a slightly different direction as well. So there are all these nested structures which are present in this Seyfert galaxy, which suggests that, and of course this is not the only example, there are several other examples, still a handful, but there are examples where nested magnetic field, nested radio outflows are seen in these Seyfert galaxies. So, so this was actually work that one of our visiting students carried out, Vaishnav Rao. And so what he did finally was to use these tools to do some kind of spectral aging analysis of these different lobes. And he found that the spectral ages of these three different lobes were 34, 12, and 3 million years. And for using this, we could derive an AGN duty cycle, which is defined like this. The time the AGN is on divided by the time on plus off. And for 2639, we could actually derive a duty cycle of 60%. So this was also very exciting. So 60% of the time the AGN is on during its lifetime. Now, the next thing was when we looked at the gas, molecular gas in this source. Now, this is an image of the molecular gas, CO gas, from the Karma Edge survey. And there was a kind of a hole that was seen in the CO gas emission of extent 6 kiloparsecs, which is kind of very coinciding very nicely with the GMRT lobes. And this is a moment 2 image of the CO map, and you see, you may not see it very clearly, but basically there is increased dispersion at the edges of this radio structure, which is seen. The bottom 2 panels are the Galax images. So this is far UV emission, and this is near UV emission. And in both the cases, we also find some kind of deficiency in the UV emission, which we suggest to be star formation quenching. And so what you're seeing is gas evacuation and also star formation quenching. But the fact that you may have increased dispersion at the edges of the radio lobes is suggesting that there is possibly both negative and positive AGN feedback, which is going on in this galaxy. And what is interesting is that perhaps the fact that it has so many different AGN activity episodes is also responsible for the fact for the reason that we see this hole in the CO gas and the star formation. It's likely one very easy way to connect all this is that possibly this AGN feedback drives gas away, and then after some time when the AGN is off, the gas comes back and the AGN is like reignited. So you kind of are able to explain both the episodic activity and the feedback in this way. So that is it's a very nice picture that emerges. So now let me talk about how improvements in sensitivity can tell you more about these low luminosity AGN. So here are a couple of images of radio optical overlays of galaxies from another sample called the KISS-R. And the blue-red, again, this is optical light from the host galaxies. You can see them. Some of them are interacting galaxies. Some of them are normal spiral galaxies, S0s, etc. And the green contours are the VLA first, from the VLA first survey. These are radio emission from these galaxies. And basically what is detected is just radio cores. And these are extremely radio faint. So they're just a few millijanskis in flux density. So very faint radio cores are observed in the centers of these galaxies. So not very impressive. But when you look at them with VLBI, very long baser interferometry, this is just the acronym KISS-R expanded here. And so let me just go through these images. So the first image is a galaxy called KISS-R 434. And what is seen is what looks like a core jet structure. There is probably a curvature as well, which is observed. The color is actually spectral index because we were able to detect this at 2 frequencies. So the spectrum is actually steep here. But what is interesting to note is that this curvature, when we observe this galaxy 4 years later, this curvature persists. So we still see the same structure in the second epoch of observations, which again tells you that this is all these features, even though they look very, they are very faint and they almost look like noise peaks, etc. I think they're actual real jets, but just weaker, much weaker. The extent of this is quite large. It's almost 150 parsec. So 150 parsec long jets are observed when you look at them with VLBI, even though the core, when you look at the VLA first data, which is arcsecond or 5 arcsecond images, you just see a point source. On the other side, there is another galaxy called KISS-R 618. It seemed to show a core jet structure, but 4 years later, the core jet structure seems to be having a different position angle in the sky, even though there is some emission in the direction of the original episode. And so this kind of structure is also very commonly seen in VLBI studies of radio loud AGN, which is some kind of nozzle precession. That is how you explain the results for radio loud AGN, which seems to also happen here. So overall, all in all, we are finding that the radio jets, even though they are weak and very not continuous, blobby, etc., they seem to show behavior which is not very different from radio loud AGN. And so one more thing was that this sample itself was selected on the basis of either asymmetric emission lines in the SDSS or double peaks. So I will tell how that also kind of now explains our results much better. We found, because we had these 2 episodes, we actually found that some of these sources had jet components moving at superluminal jet speeds. So this was one case, KISS-R 872. So this is the core and this is the jet component J0. And between 31st December 2018 and 5th November 2022, the jet component seems to have moved at 1.65, of course, with a large error times C. And then this is not the only source. We found another source, KISS-R 102, which also had these 2 compact components, which were kind of close to each other, which also seems to be moving marginally superluminally. So there seems to be also the existence of fast jets in these radio quiet AGN, which is also a little bit unexpected. And again, I want to stress that usually, till very recently, you wouldn't have looked at these AGNs with VLBI and actually detected jets. So it's because of sensitivity improvements that you are able to do this kind of work. And usually radio quiet AGN are not even followed up with VLBI because they're so dim that they're not really followed up. Radio loud AGN are typically followed up on a very regular basis. So this is making the case that we should be also monitoring the jets in radio quiet AGN. Now, because these sources were actually picked up on the basis of spectra, we were able to model the emission line data, and we use this plasma modeling code mappings, which is kind of shown here. For example, here these are line ratios O3 by H beta and S2 by H alpha, and similarly you can have N2 by H alpha and O3 by H beta. Now the color that you see, the color grid, is actually produced from different models, and the data itself is here. The line ratios are here, and different models are kind of compared with the data to see what fits. And what was interesting to find was that this model, called shock plus precursor model, actually seems to explain the emission line data for these sources, especially the sources which had VLBI jets reasonably well. Now, what this model is, that it's saying that it's not the shock from the jet itself which is ionizing the emission line gas, but rather the post-shock gas, the gas which is kind of undergone a shock, which then emits UV and UV emission and soft X-rays, and then photoionizes the surrounding medium. So this this is another way to say that even though these jets are weak, they are impacting the emission line gas clouds around them. So they do things, even though they're tiny, they're doing things around their neighborhood. Now, this is there are some other cases as well in the literature where this has been found, and so this is 25, no? 4 minutes, yeah. The other cases, this is one such case. So this is a radio quiet AGN J1316. You see in contour here. The two panels here are, the color is actually showing you data from VLT Muse, and this is O3 emission. So here, this is just total intensity, and this here is the dispersion again. So what is seen in this case, this very small, it's just a kiloparsec long core jet structure. But you see how O3 is enhanced at the edges of this small jet. And also the dispersion is enhanced in this direction, perpendicular to the jet. Similarly, in the CO emission, this is from ALMA, there is an increased amount of CO, of course, but there is also increased dispersion in the direction perpendicular to the jet. So these small scale jets seem to be impacting the gas around them, not just the ionized gas, but also cold gas, etc. And so they are, carrying out feedback. There is also the teacup quasar, which has been found to kind of follow this behavior as well. So this is also in keeping with these hydrodynamic simulations that have been carried out by several authors, including Dipanjan and group, where they find that in the radio quiet AGN, there is an existence of both positive and negative feedback happening on these very small scales as the jet kind of emerges from the black hole. Okay, so now let me just put everything together. So what I wanted to stress in this talk was that radio quiet AGN or low luminosity AGN, I'm using this term interchangeably, they make the vast majority of active galaxies and likely show episodic activity, which of course requires high sensitivity to detect these past episodes of activity from these sources, and that is where GMRT and in the future SK is going to play an important role in picking up all this from the past activity episodes. And it's also possible that maybe all galaxies go through this kind of active phase, and this is actually in keeping with the results that are coming out from the Event Horizon Telescope for the Milky Way galaxy and the presence of the Fermi bubbles in the Milky Way. That maybe the Milky Way was active also at some point. And it looks like from the work that we've done on polarization that magnetic fields could actually be important in the production or collimation of these radio outflows, even in the very weak jets of radio quiet AGN. And this has profound implications for the radio loud, radio quiet AGN divide. And these outflows, even though they're weak, they seem to still influence their surroundings. So they are being agents of AGN feedback. And SCAR with high sensitivity at low radio frequencies especially is going to really improve our understanding of low luminosity AGN in general. Thank you.
Okay, we have time for a few questions. Okay, here. Preeti, so the slide you had the rotation measured. So is it that looking at the winding of the magnetic field, you can figure out that how fast is the spin of the...
We haven't done that.
And then you can also look at the H1 spectra along absorption along that and cross-check if you get a similar velocity dispersion.
Sure, that's a nice idea. So H1 spectra, you would expect, you mean gas rotation or something? Yeah, thanks.
Hello. In your initial slide, you showed the result of KISAR 434, where you showed this bending Z.
Yes.
Can you go, please, that slide?
Yes. Sorry. Yeah.
Yeah. So, therefore, how do you know that it is associated with the AGN is not the separate source?
Okay. So these are VLBI images. The field of view of the VLBI images is actually very, very tiny. So it's going to be all associated with this one single source.
Okay. So
you're looking at a very small piece of the sky. So this is all, whatever you see here is all associated. Is your question about binary?
It's very it's just a milliarc second.
Yes.
Scale. Okay.
Yes.
Good.
Yes.
Do we expect time variability in this radio quiet AGNs?
Yes.
And if yes, what would be the time scale of?
Yes. So time variability is actually observed already, and depending on what scales you are kind of looking at, on the arcsecond scales, it's kind of few months. On smaller scales, of course, it's slightly faster. But we haven't actually. We did look at. I have actually looked at the variability in these, and so in the few years, of course, there is variability. There is variability for sure, and it's like of the order of like maybe around 25% or so.
So what are the redshift of these sources that you are getting?
Okay, so they're very, very close by. I don't remember the individual ones, but maybe like 0.01.
So any of them has been observed with Fermi?
No. These galaxies, especially from this particular sample, are actually not very well studied at all. But no, yeah. But why do you want to know that?
Because like I wanted to see how the multi-wavelength like emission and the variability looks for these sources. Because they seem very faint and
yes.
And the statistic is very poor, so I don't know how conclusive this will be, only the radio emission.
I see. I did want to say, because you asked not about these sources, but for example, NGC 1068 is actually detected with Fermi. It's one of those sources which actually has been, it's a small jet. It's also not very radio bright, but it has actually been detected with Fermi. So, yeah. So whatever you're suggesting could be done, looked at.
Narendra. So these as these galaxies are like nearby, so have anybody looked into their ISM in neutral gas, for example, if there are effect of feedback in them?
We haven't done that. I don't think there is much work done yet on these galaxies, but yeah, that should be looked at.
So, Preeti, I have a related question. This one case where you showed the dip in the molecular gas distribution.
Yes.
Is that 12 CO or 13 CO? Because
that's a good question. I don't remember that.
Because in the
NUV, CO10.
Because the NUV, the dip is probably not that significant. Looking at least this image.
So you see, there is a ring here in the UV, and this emission here we think is from the AGN itself. But there is a ring here which is probably seen much better in a grayscale image than this. And here also, I think that the ring is not so pronounced, but here again you expect dust to be present. So.
Okay. Any other question? We still have time for one more question, maybe. Okay, you mentioned that the superluminal motion in this case are not expected. Is that
yes. Yes.
Why is that? Because if the mass of the black hole or the spin is sort of similar to the other cases, then velocity will not. I mean, the mass loading or momentum may be different.
Yes.
But the velocity will be.
So that's a good question. So I think it is generally there is a consensus that radioquiet AGN jets are very slow, weak and slow. because it's normally, I think before this, there was only one, that is not even a proper Seaford galaxy, but 3's Wiki 2 was the one, there was a claim that there was something very fast jet-wise. The issue, I think, has only been that these sources have not been, VLBI at multiple epochs has actually not happened for these. So there are only a handful of sources where people have done it. They have found not very high speeds. But until you follow them, you won't see it. Because also the point is that it's not that the jet is constantly moving at that speed. It's just one jet component which is moving fast. So to pick up that, you will need monitoring. Yeah.
Okay, so if there is no other question, let's thank Preeti and we move to the next talk of the session.